Hi, this is Rick Tharp of RX Kinetics with another Antibiotic Kinetics program demonstration. And in this installment I'd like to give you an explanation of the model database and to demonstrate the model editor. So we begin by clicking File on the menu bar and then Edit Drug Models. That brings up our drug model editor. Across the top is the data bar. Just explain what these buttons are. The first four buttons are used to navigate through the database. You can move through one record at a time using the next and previous buttons. You can skip to the last record or skip to the first record with those buttons, the skip buttons. The next button is the carbon copy button. And this functions to copy the current model to a new model, and we'll be demonstrating that in a few minutes. Next button is the Add function, and we'll just click on it and show you that. When you click the Add icon, it clears out the input so that you can enter a new model from scratch. Let's cancel that. Next button is the Inactivate button. Looks like a minus sign. Click it, and that model then becomes inactive. It doesn't show up in the drop-down box when you select the model on the prospective or retrospective tab. And you can see that how an inactive model is designated when you're browsing through the model database. So to reactivate, that's what this button here is, a little plus minus on the button. Click that to reactivate. The next button is Save, and the last button is Cancel. So if you're editing along here and you realize, oops, I made a mistake, you can click Cancel and that restores the record to its original state. Now I just want to go through and describe each of the fields. The first field is the model name and date. That must be unique for each model. Next field is volume of distribution in liters per kilogram. The next field is correction factor, and that is the correction factor for determining dosing weight used to calculate the volume of distribution. Now let's move to an aminoglycoside. Might give you a little better example. So the correction factor is that percent of weight above lean body weight that's used in the dosing weight calculation. For example, aminoglycosides do not distribute well into adipose tissue. Therefore, most clinicians use a 40% correction factor for aminoglycosides. So 40% of the weight above lean body weight is then used in the dosing weight calculation for aminoglycosides. If you want to use total body weight, just use this, change that to 1. But for aminoglycosides, most clinicians use 40% correction factor. The next field is target peak. The next field is peak predict time, and that is the time in minutes after the end of the infusion when you are targeting your peak level. For the aminoglycosides, or drugs that rapidly distribute, the peak predict time is 0. For drugs like vancomycin, which distributes slowly, you want to target your peak level at 60 minutes after the end of the infusion to avoid the distribution phase. Next field is target trough. Next field is infusion time, and that's a drop-down box. You can choose 30, 60, 90, or 120 minutes for your standard infusion time. The next field is the extended interval dose in milligrams per kilogram. And this is only applicable to aminoglycosides. The EI dose is also referred to as pulse dosing or once daily dosing or Hartford nomogram. So for aminoglycosides you would set that. For drugs like vancomycin you would zero that out. It's not applicable to vancomycin. Okay, the next fields up in the upper right hand corner is KEL or CL, and you select either of these to choose which parameter the model calculates, either a rate constant or a clearance. And that's using our two different vancomycin models. The KEL model calculates a rate constant. The CL model calculates a clearance. And that brings us to our next two fields, the non-renal and renal KEL. And those are the portions of the KEL equation. So those are best described by looking at our KEL equation. And let's look at a page from the PK tutorial on the RX Kinetics website, which shows the relationship between creatinine clearance and overall drug elimination. So on the y-axis you are looking at the observed rate constant versus creatinine clearance. As you can see, as creatinine clearance increases, so does the elimination rate. And the slope of that line, determined by the regression analysis, is your renal portion of the KEL equation, and the y-intercept is a non-renal portion of your KEL equation. So here's your equation. Elimination rate equals the non-renal plus the product of your renal times the creatinine clearance. The next two fields are pediatric dose and pediatric interval. And in this program, the pediatric patient is defined as a patient from 8 days to 12 years. A neonatal dose and neonatal interval are next, and those are defined as patients who are 1 to 7 days old. Reason being that in some drugs, neonates don't clear as well as peds. For example, vancomycin. The dose, you give them each 15 milligrams per kilo, but in a peds patient you would give it every 8 and a neonate every 12. And I'd just like to mention here that, or remind you that prospective dosing is weight-based in peds and neonates. And the reason for that is the inaccuracy of creatinine clearance estimation in these patients doesn't permit you, or doesn't allow you to create or to accurately determine a model. Therefore, it's better to prospectively start a patient out on a weight-based regimen and then draw serum levels and adjust from there. And finally, the last field on a drug model record is the permit serum level analysis checkbox. And this is simply a yes or a no. And the reason this is there is you can use this program for not just for aminoglycosides or vancomycin, but you can use it to dose other drugs, for example, ceftazidime or other beta-lactams. You can search the literature and come up with a population model that you may be able to more accurately dose these patients in renal impairment if you have a one-compartment model instead of a nomogram. And since you can't routinely order a ceftazidime level, you would leave that unchecked. Unchecking that box means that that drug will not show up under the prospective models. Retrospective models. Excuse me. We'll look under prospective, we'll see ceftazidime does show up there. We look under retrospective or serum level analysis, and you'll see ceftazidime does not show up there. That's because that's not a drug that we routinely order serum levels on. Therefore, that box is unchecked. So now I'd like to just go into a quick demonstration of how to add a model using a current model as a template. Well, first let me edit this amikacin to say med-surg. Click Save. Now we want to create a model. Say we have a model that we use at our hospital for obstetric patients. And in our experience, we've found that these patients have a larger volume of distribution than a general med-surg patient. So we'll copy the amikacin model, come up with a unique name. We'll go in here and zero out peds dosing. It's not appropriate for peds. And click Save. Now we have two models. We have an amikacin med-surg model and an amikacin OB model. And we can take that one step further. Let's say we have a burn unit, and we know that in our burn patients, they also have a larger volume of distribution than our general med-surg patients. So we create a unique name, describes the model, and now we have three amikacin models: a general med-surg model, a burn model, and an OB model. And you can see that those are going to show up here in your drop-down box now. Now we have three models, both in our prospective and our retrospective tab. So that's an overview of the drug model database and how to use the model editor in Antibiotic Kinetics.